I mean, it's a great pleasure and honor to be here and celebrate Raf's contribution to science and to our own work and career. And I'm happy to see my teachers here and the friends. And I'm going to talk about the near-term application of small-scale quantum computing. And I took a course about 30 years ago in classical information theory from Rafi. And just to put things in a general overview, we have classical computing, which is based on binary system, like analog, digital, and mechanical. And I will talk about the quantum, which is based on qubit, quantum bits, which is a superposition of 0 and 1. And we have 4 major ways to do quantum computing. I will discuss quantum gates and adiabatic quantum computing, but also we have one-way quantum computing and topological. One way you start with entangled cluster of states, and you do measurement along the way, and each time you do measurement, the system collapses. And this is one way, you cannot go back. And topological is encoding information in the topological state. And it took me a while to understand why people drink coffee when they have donuts. They are the same state. The field is moving so fast that almost a day you have like 30, 40 papers in the field. And just to give you an idea how fast we are moving with this field, back in 2010, we established an initiative center for chemical innovation at Purdue, and the idea was to focus on quantum information for quantum chemistry. So phase 1, we have with us 4 schools, and we are focusing on quantum information for chemical systems, quantum algorithms, and quantum control. And the phase 1 was for 3 years, and the idea to go to phase 2. And for phase 2, we put together, people from 10 schools, and almost all these people working in the field of quantum information, quantum computing, and also we were lucky, Dudley said he will do the educational part, try to educate the public of the importance of this field. We did not succeed in phase 2, and this was 2014. And the panel said, we don't have a quantum computer, and it doesn't seem worth, in a quote, to invest 20 million in a device that will not have in 5 years. And then things changed. If you look at the field for the last 2-3 years, things changed dramatically. And the reason for that, now the industry are taking the lead. And if you look at this report from April 2017, the Homeland Security Research, they talk about the 18 major companies and the investment in this field of quantum information, quantum computing, and they project that the market will reach about 10 billion in 2024. So back if you look at this field in '94, the field got excitement because of the factoring algorithm of Shaul. And the last 2 years, now the industry is building strong quantum information computing group and are leading the field, mainly IBM and Microsoft. And all of us have seen the recent reports about Google reaching 72 qubits and IBM 50 qubits. And the argument, like if you have a machine with 50 qubits, you can reach quantum supremacy, which means you can do calculation on this machine that you cannot do it in a larger supercomputer. Okay, now you see there's a shift in this field from can we build this machine to what to do with the machine. And in chemistry, the question is, what are the challenging problems in chemistry that need such a machine? And if you look at chemistry, it's a very complex field, but one can look, for example, on a specific problem in complex biological systems, like to understand photosynthesis, how birds finding their magnetic north, or in catalysis, like the nitrogen fixation, how you go from nitrogen to ammonia, mimicking what this process in nature and not the industrial process, or material design, drug discovery, optimization. All these problems are very complex and cannot be done accurately on a classical machine. And we all know in computational chemistry the way it works. First, you have to get the structure, which means you have to do electronic structure calculations accurate enough to produce forces which allow you to do dynamics. And if you go back to 1929 with the quote of Dirac, we have equations that we are familiar with, and the question is, how do you solve these equations for electronic structure? And we are lucky in the field, we know the equation, the second order linear differential equation. This is the Schrödinger equation, and this is the equation whose grave. So we know the equation, we know the forces, we know everything, we know the equation, but we don't know how to solve it for large number of electrons. But this is not a new field. We have doing research in this field for the last 80 years, and great minds put a lot of effort in this direction, and we have accurate like ab initio methods, semi-empirical, density functional, and non-conventional. And here I add the contribution of Prof in algebraic methods. And you see, okay, what is the challenge? What is the problem with this field after these 80 years of research? And the problem is very, very simple. We have to reach chemical accuracy on the order of 1 kilocalorie per mole. And if you try to do accurate calculation, let's say with full configuration interaction, you see the cost is exponential. So you have to come up with an algorithm which speed up the calculation from exponential to polynomial. And this is the promise of quantum computing. So if I draw the analogy, if I go back 60 years, and in the early 50s, when we invented the classical computer in the 40s, people like Boyce was the pioneer of designing algorithm to solve with that classical machine. And now 60 years, now we have quantum information, and this is our results from IBM machine. And they did potential energy surface for small systems. So you see the analogy. Now we have a quantum computer, and people are really pushing the application of this into the quantum chemistry. So what we have in the gate model, what is the gate model? The gate model, you would like to transfer your problem as electrons, you have fermions. So you go from fermionic operator to Pauli spin operators. And there is a well-known transformation from fermionic system to spin operators. And then you go to second quantization, so you present the wave function. And mainly to get the spectrum, there's a well-known phase estimation algorithm developed by Seth Lloyd at MIT, which allows you to get the phase, which is the energy of the system. So what we have so far, we have small systems like diatomic systems. And these systems already, we have a well-known theoretical and experimental results. So this is summarizing the gate model. And the question is, in the gate model, how do we design things with scale up for large number of electrons? Now, the other approach is the adiabatic quantum computer. And for this, we have the D-Wave machine, which is a Canadian company, and they have 2,000 connected spins on a chimera graph in a certain configuration. So this is not a universal machine, but it's a specific machine for optimization. And the question, can we transfer the electronic structure problem from fermionic Hamiltonian into something that the machine can take it and do the calculations? Why we have to do that? Because the machine is built on the Ising Hamiltonian. So you start with the initial Hamiltonian that you know the answer, and you do adiabatic evolution, which means you have it slow enough so the system will not jump to the excited state. And at the end, you encode the information in your Ising Hamiltonian. These are nearest neighbor spin interacting with the coupling J and external field H. So the question, can we transform the fermionic system into the spin operator, into the Ising type Hamiltonian? So we succeed to do this transformation. This is exact transformation, and we just published it recently in this special issue of Ben Widom. I will not go into the detail, but the basic idea, you to expand the Hilbert space. The problem fermionic operator in certain space, when you expand the Hilbert space, you can transform it to Ising. And this is exact transformation. Now, these coupling in the Ising and the field are related to the 1 and 2 electron integrals. But this is an exact mapping in higher dimensional space. Now we have Ising. We can go to the machine and run the machine and get the electronic structure calculations going with the D-Wave. And we did it for these small systems because, like, if you do calculation for H2, you need 50 spins, and for lithium hydride, you need 267 interacting spins. And this is the configuration. You have to map your full connected graph to what we call the chimera graph in the D-Wave machine. But in principle, we can do the calculation. Now you can say, okay, chemistry is not about H2 and the atomic system. How do you go to large molecular systems? And here, for example, if you look at the special issue in Nature about the chemical space, if you just examine organic database with 13 atoms, you see the space is 10 to the 60 molecules. And the question, how do you go bridge the gap from a small system to such large, and this is only organic molecules. And if you go to the full chemical space, we talk about larger than 10 to the 80. So we thought about maybe about this point, we can think about merging the classical machine learning with the quantum computing into the new algorithm of quantum machine learning. So we have quantum computing. We already talked about the machine and how one can run this calculation. And we in the quantum computing, and we have the machine learning. People do it, and this touches every aspect of our life. And the question, how do you combine both to do calculation for large systems? And the idea is to merge the two fields into quantum machine learning. And what is the promise? The promise is speed up. When you go to quantum, you have an exponential speed up over the classical computing. For example, if you have terabyte of scaling, you have 10 to the 12. When you go to the qubit, you take the log, it's only 40. So 40 qubits is going to manipulate 10 to the 12 bits of information. So this is the picture of what the promise of quantum computing is, the exponential scale up of these data. So what is quantum machine learning? I mean, the traditional computing, you have data, you write a program, you give it to the computer, and you have output. In machine learning, you look for correlation between the output and input, and you design a program. And the idea is you take this program back into the traditional machine. The quantum machine learning, you turn all the computer, the classical computing, into quantum computer, and the program into the quantum program. So you do quantum machine learning with the idea of scaling this information. And let's just look at what we do in quantum chemistry. If you do the accurate calculation for this simple system, the aspirin, it's about 20 atoms with 100 electrons. If you're looking for accurate calculation, 1 kilocalorie per mole, you talk about years of CPU time. So what we'd like to do, we'd like to do machine learning, which means you have to do accurate calculation at the lowest computational cost. And if you look at the development of this field, I mean, here we have 3 Nobel laureates, so we have 6 Nobel laureates are trying to figure out ways to do calculation, simplify the electronic structural calculations and solve the Schrödinger equation. So what we did with the quantum machine learning, we said, okay, we have to build a quantum box, which takes an input configuration of the electrons and output the wave function. And again, in quantum computing, you are not supposed to touch this box. The other minute you open it, the system collapses. So you have to design an algorithm which will allow you to calculate the wave function. And the idea is to go to Weizmann machine, which takes the energy as an Ising-type Hamiltonian. This is the visible where you would like to train your data, and these are hidden, will allow you to move with the weight, to adjust the weight in order that your distribution from the Boltzmann will match the wave function of the system. So just to make the story short, we have done this one for electronic structural calculations. And the main point was you have to make sure the sign of the wave function is correct, so you can predict not only the amplitude, also the phase of the wave function in this machine. So we have done this one calculation, and we get the results for simple systems from the Boltzmann machine. And we are using this symbol because we have up to 16 qubits to play with for these quantum calculations. So the other, I will not go into detail, but what really exciting about this field, that we have found out that if you look for factoring a large number, which is important in the security, finding the 2 prime numbers, you can map it to an Ising Hamiltonian, And it turns out, if you solve the Ising Hamiltonian for factoring, the ground state of this simple system encode the factorization, the two prime numbers. And it's really exciting to understand what is the physical system that if you factorize it, the ground state of this system really encoding the information for factoring. And since also our electronic structure moved to Ising, the question is what is the correlation, or if there is any relationship between the electronic structure which we map to Ising and factoring can also map to Ising Hamiltonian. And we run this calculation. These are the, for example, if you factor 15, this is the J coupling in the Ising, and this is the H. And we run it also in the D-wave machine, and my student got the factor, the 3.5, which factor 15 is the ground state of this Hamiltonian. Now we are factoring large numbers in this machine. Again, all these are mapped to Ising type Hamiltonian. And it's really exciting to understand the physics of this problem, why certain systems encode information about the factoring numbers. And people ask how many spins you need to start breaking the code. From our scaling, we need around 150,000 interacting spins. You can see, you can breaking the code. So now, what is for the future? The future is really to go for open quantum dynamics, where you have to come up with an algorithm to solve the master equation in a quantum computer, because most of the interesting problems are you have an environment, and the question, how do you add the environment to the system? You need to solve the master equation in a quantum computer. And happy 80th birthday.